Sensors which are not embedded are subject to wear and tear from their environment and require regular maintenance. Even embedded sensors need to be accompanied by batteries, which also requires maintenance, as well as being a fire hazard and not suitable in high or low temperature environments. We sought to address this problem in our project by developing a wireless data acquisition system that is powered off radio frequency or RF waves. The specific system we designed was for our sponsor company Mesomat. Mesomat is a startup who makes stress-strain sensors for their industry partners, which operate on the principle of piezoresistivity. Essentially, their sensors change resistance when stretched or bent. They are currently powered by batteries, and our solution was created to see if their sensors could be powered with RF waves, as well as wirelessly return the sensor measurement for embedded applications.
The high-level architecture of our system consists of four key elements: power harvesting for providing power to our circuit, voltage regulation to ensure that the power supplied to our circuit does not damage it, data acquisition to perform the measurement and transmit it wirelessly, and decoding to convert the received information into a meaningful format. The power harvesting, voltage regulation, and data acquisition all take place on a custom transponder PCB shown here, which collects wireless power, performs a measurement, and sends back the data to the home base, which is not shown here. Meanwhile, the decoding takes place at this home base, more formally known as the transceiver, which transmits RF power wirelessly to the transponder and then decodes the information received from the transponder. Let's dive a little deeper into each of these key elements now. Our power harvesting design is based on the Dixon charge pump, which consists of a series of diodes and capacitors chained together, as shown above here. This circuit converts a small AC signal into a large DC voltage. In our case, the AC signal fed into this circuit is from an STM transceiver that we programmed to output a continuous RF signal. A voltage regulator is needed at the output of our power harvesting circuit because the microcontroller on the transponder can only operate between 1.8 volts and 3.3 volts. We decided on a boost buck converter for our voltage regulation architecture, which consists of an inductor and capacitor configured in parallel with the load, along with a transistor that switches between two modes, one where magnetic energy is being stored in the inductor, and another where the inductor supplies current to the capacitor. The regulated voltage then depends on the duty cycle of the switching transistor. By the time our RF signal reaches the transponder, its amplitude is typically on the order of a few millivolts. However, thanks to our power harvester and voltage regulator, we were able to convert this into a steady DC voltage of approximately 2.5 volts, even with a few centimeters of distance between the transceiver and transponder. The actual measurement of Mesomat sensors is performed with the analog to digital converter, or ADC, of an MSP430 microcontroller. This is achieved by configuring the sensor in a simple voltage divider network, where the sensor acts as a variable resistor between two reference resistors, as shown here on the left. Once this measurement is acquired, we used an IR LED on the transponder and an IR receiver on the transceiver to send back this data wirelessly. Since the ADC already converted our measurement into a 16-bit binary signal, we programmed the MSP430 in such a way to encode each 1 bit in the binary sequence as a high-frequency burst, which is the format expected by the IR receiver, as shown here on the right. This encoded signal is then fed as input into the IR LED, which then transmits the signal to the IR receiver. Finally, in order to convert the signal from the IR receiver into meaningful information, an ESP32 microcontroller is used to sample this signal, and then a decoding algorithm is implemented in MATLAB so that a single 16-bit packet can be extracted from the signal and converted from a binary sequence into an actual number. An example of this decoding is shown here, where the extracted packet is seen on the bottom right, and the value it corresponds to is found on the bottom left in its binary, hexadecimal, and decimal representations.
Initially, the plan was to transmit and receive data through RF as well. However, due to the prevalence of RF interference in all testing environments, along with the difficulty encountered while trying to implement RF backscattering, this was changed to IR, and the project can still have the embedded applications discussed previously, with the addition of something like a window, for example, to account for IR line of sight. In the end, the project served its purpose as being a proof of concept for the company to test the wireless data acquisition in conjunction with their sensors. The system was able to accurately and reliably measure resistance from up to approximately 10 centimeters away.